In this lecture, I want to talk about antiderivatives, which it's basically the opposite of taking a derivative. So, for example, if I had the function 2x, the antiderivative would be a function, we'll call it capital F, and it would be such that the derivative of big F would equal little f. In other words, there's a function that I can take the derivative of that will give me 2x. So just should be familiar enough with derivatives to know, to kind of work backwards and say, well, what could I take the derivative of to get 2x? And so hopefully makes sense that x squared does the trick, right? We take the derivative, we get 2x. But one thing to note here is that x squared isn't the only function that would give us 2x when we take the derivative. If I had x squared plus 1, that would also give me 2x. I could have x squared plus 11. That would also give me 2x when I take the derivative. I could have x squared plus pi, and I take the derivative of that. So in general, the most general antiderivatives, these are all antiderivatives, but the most general antiderivative would look something like x squared plus c, where c is any constant, right? I can add any constant to x squared. When I take the derivative of it, I get 2x. All right. So graphically, a way to think about this is, so we know that x squared looks something like that, right? What if I had x squared plus 1? Well, that would look, it should look very similar, right? Except it's moved up 1. What if I had x squared minus 5? Then it would look very similar, except it would be down here. Or x squared plus 10. That would be very similar, except it would be up here. So notice that, let's say right along this point here, if I were to draw in tangent lines, the slopes of all those tangent lines, they're all parallel, right? So the slopes of the lines, the derivative is the same at that point. The equation of the tangent line is different, right? They would all have a different y-intercept, all right? But the slopes are all the same. So that's where this plus c, it's just a vertical translation, right? It takes our x squared and it moves it up or down. But the point is that any given point on the graph, the slope of the tangent line will be the same. All right? So that's kind of another way to think about why we have this plus c on there in terms of graphically, why that makes sense. Okay, so now that we see what an antiderivative is, let's look at how we might find antiderivatives of common functions. So the other thing before I go through that real quick, I want to talk about is some notation. So if we have, for example, y equals some function f, then remember dy dx is another way to write the derivative, right? So what we're saying here, well, real quick then, remember our differential notation, dy equals f prime of x dx. So f of x, so here's the notation, f of x, which is the antiderivative, we use this notation, it's called an integral sign. So it's the integral of, well, technically this would be f, right? Little f, it's the integral of the derivative, right? We're calling it big F up here, but the point is an antiderivative is the integral of the derivative. It gives us back little f if we take the antiderivative of f prime. Another way to think of it is if big F is an antiderivative then of f, then we have this. And this is the notation that you will see quite a bit, where you just have this integral sign with the function, and this is basically saying you're taking the derivative with respect to x. But this is where the notation comes from. So for example, we could say, what's the antiderivative of x cubed. Antiderivative, I should say, antiderivative is basically the same as the integral or the indefinite integral. I'll just put that here, indefinite. Meaning it's indefinite in the sense that there's a number of different antiderivatives, depending on what we put in for c. So the antiderivative of x cubed, we're looking for a function whose derivative is x cubed. So it makes sense that it would be of x4 of the order 4, right? Because if you take the derivative of this, you're going to get an x cubed up here. The issue is if you take the derivative of this, you're going to get 4x cubed, and we just want x cubed. So how can we lose that 4 when we take the derivative? Well, when we find the antiderivative, we can divide by 4, right? So now when I take the derivative of this function, I multiply by 4, that cancels this 4 here, and then I'm left with x cubed, all right, plus c. So in the same way with the power rule, if we had x to the n and we took the derivative, we multiplied by n and then changed the power, we subtracted 1 from the power. Here, if I'm going to take the antiderivative of x to the n with respect to x, first I add 1 to my power. That's where the x to the 4th came. But in order to get back x cubed, I had to divide by my new power, right? And so that when I took the derivative, they would cancel. So I'd get m plus 1. So I take my power, I add 1 to it, divide by that new power, and then don't forget about your plus c. All right? So that is how we do antiderivatives of power functions in general. This is kind of our power rule for antiderivatives. Okay, let's look at something like the indefinite integral of x squared plus 3x plus 2. All right. Well, just like derivatives, we can find this just by doing them separately. I can take the antiderivative of x squared plus the antiderivative of 3x plus the antiderivative of 2 dx. Now here, if I just use the power rule for integrals that I just talked about, I'm going to get x cubed over 3. All right. And then here, one thing I want to point out here is that this is the same as, if I want to look at something that takes the derivative of to get 3x, then that's the same as 3 times the antiderivative of x. All right. So this, we can use our power rule, that's just x squared over 2. All right. And then here, well, what do I take the derivative of to get 2? Well, that would just be 2x. All right. Now, technically, there would be, I'll put this in here, there would be kind of a plus c here, and there would be a plus c here, and there would be a plus c here. But it doesn't really matter because each of these c's can be anything, so we could just as well write our answer as x cubed over 3 plus, and once I simplify this, I'm going to have 3 halves x squared, and then plus 2x plus c. Since these can be anything, we can kind of combine them into 1, which also can be anything. So a takeaway from this example is that if I have something like a polynomial or any kind of combination of functions, I can just find the antiderivative of them, each of them separately, and just add on 1 plus c to the whole function. Okay, so that was a different example. Let's look at something like, here, pick a different color for a new example, the antiderivative of the square root of t dt. All right. Now, one way to think about this is, what would I take the derivative of to get the square root of t? But another way to do it is just to rewrite this as a power, because we have this convenient rule to find the antiderivative of a power function. So if I rewrite this t to the 1/2 dt. All right. Now what I'm going to do is I will add 1 to the exponent. So that will give me t, and 1/2 plus 1 is 3 halves. And now I divide by my new exponent, which is 3 halves, plus c. Well, that's kind of ugly, so let's clean it up a little bit. Dividing by a fraction is the same thing as multiplying by its reciprocal, so I get 2/3 t to the 3/2 plus c. All right, what about something like the indefinite integral of 1 over x to the 4th dx? Again, we could think about what would I have to take the derivative of to get 1 over x to the 4th, or I could rewrite this just as x to the -4th, right? Because now, again, I can use my power rule for antiderivatives. We have to be careful here, though, when we're working with negatives. I'm going to add 1 to the exponent, so that's going to give me -3, because I'm adding 1, and then I'm going to divide by -3, my new exponent, plus c, or -1/3 x to the -3, just to clean it up a little bit. Okay, next example should be pretty straightforward. Integral of sine of x dx. What do I take the derivative of to get sine x? Well, let's just say we know it's going to be something with the cosine x, right? But it's not exactly going to be cosine, because derivative of cosine is negative sine. So how do I offset that negative so I end up with positive sine? Well, of course, I have to put a negative here, right? Now when I take the derivative of cosine, I get negative sine, plus this other negative gives me the positive sine, plus c. Another example, the integral of 2 over x dx. This one's a little bit tricky. It's not like these where I have 1 over x to some power. And why is that? Well, let's first bring the 2 out front like we did up here, so we can kind of see what we're working with a little bit better. It's 2 times 1 over x dx. All right? Now, it might be tempting to rewrite this. We could rewrite this 2 x to the -1. That's what I said to do up here, right? Rewrite it. The issue is what happens here. Let me just kind of in a different color. I'm going to write it in red because this is not going to work. All right? I add 1 to the exponent. I get x to the 0, and then I have to divide by my new exponent, which is 0. So that's undefined. This doesn't work, right? Because I can't divide by 0. Let's back up here for a second and look here. That should look familiar. What do I take the derivative of to get 1 over x? Hopefully it's coming to you and you are saying that that looks like the derivative of natural log. And that is indeed what it is. So we have this 2 natural log of x plus c. Now, the other thing I have to point out here that's a little bit tricky is that I actually need to have an absolute value on this. And the reason for that is that the domain of the natural log function is, well, so the domain for natural log is only good for x greater than 0, all right? But 1 over x could have negative values of x. And so in those cases, this wouldn't work. But if I take the absolute value, then I know that whatever I'm taking the natural log of, I can actually find a value because it will be within the domain of natural log. So you'll see this absolute value, and the reason for that is because of the domain of natural log. Okay, one more example. Let's take a look at something like 3x cubed minus 9 over x squared. All right, now this one looks more complicated at first. The trick is to rewrite this. All right, so if I only have a single term in the denominator, I can rewrite this as 3x cubed over x squared minus 9 over x squared, right? This is basically the common denominator in reverse, right? So I can separate this out into 2 terms that I could combine because of the common denominator. I'm just going to go backwards here, take the integral of this, because each of these simplify, especially this one here. So this one simplifies to, so now I'm looking at the integral of 3x, and I'll rewrite this one, like I said, as x to a power negative 2. Okay? Because the x cubed divided by x squared just gives me the x. Here I'm going to take this x squared in the denominator and rewrite it as x to the negative 2. Now I can do them separately, and I can just use my power rule. So I'm going to have 3 times the integral of x dx minus 9 times the integral of x to the negative 2 dx. So this will give me 3 times x squared over 2 minus 9 times, that's going to become x to the negative 1 over negative 1. I'll have this plus c on the end of the whole thing. So let's clean this up a little bit. That's going to be 3 halves x squared divided by negative 1. Just makes this negative, so it'll make this positive. So I'll have plus 9 x to the negative 1. I could rewrite that as 9 over x if I wanted, and then plus c. So here the trick is rewrite the integrand. That's a new word. That just means this piece right here. This piece that I'm actually taking the integral of. The function that is the derivative of the function I'm looking for is another way to think of it. So rewrite the integrand, try to simplify, and then take the integral. Okay, last thing I want to talk about is something called a differential equation. All right? So differential equation is just a big word for an equation that includes a derivative. So we've already actually been looking at things that are differential equations. So for example, if the derivative of f equals 6x, and I want to find f, then I take the antiderivative of 6x, all right? That's going to be 6 times integral of x dx, which is going to just give me 6 times x squared over 2 plus c, which simplifies to 3x squared plus c. Okay, so we've just solved a differential equation. But we can also find, if we're given what's called an initial condition. All right, so an example of initial condition is maybe they tell us that f of 0 equals 8. All right, f of 0 equals 8. Then we can find what we call a particular solution. All right, so what do I mean by that? Well, if we go back to this little graph that I drew at the beginning, these are all solutions to, well, here we're basically saying that we said that the derivative, I guess we could, our differential equation here is f prime of x equals 2x. So that means that f would be a general equation, or general solution, I should say, would be f of x squared plus c. But if they tell us, if they give us this, in other words, what we're saying here is that the point 0, 8, only one of these curves would have the point 0, 8 on it. And then we can nail down which one of these curves is our particular solution. So let's look at how we would use that to complete this problem. So here we're saying that this is f of x, right? This was f prime, so this is f. This is the function I take the derivative of to get 6x. So this is telling me that f of 0 equals 8. So I have two expressions now for f of x, or at least for f of 0. I can use this and say, well, f of 0 equals 3 times 0 squared plus c. But I also know that f of 0 equals 8, so that equals 8. Well, that just tells me, well, that obviously is 0, so that just tells me that c equals 8. So now I know my particular solution is 3x squared plus 8. I have a very specific equation, not just this general equation where I could just add anything onto it. All right, let me give one more example of solving a differential equation, one that's maybe a little bit more complicated than the one that we just saw. So let's take a look at something like, we know the second derivative now. Here we know the second derivative is x. They tell us that the second derivative, the first derivative. Sorry about that. The derivative of f evaluated at 0 equals 1, and the function value at 0 is 0. All right. So we want to find a particular solution. They're giving us two initial conditions because we're working with the second derivative here, and we want to find the particular solution for f of x. So the first thing is to recognize that there's this relationship between f prime and f double prime where the second derivative is the derivative of the first derivative. So the way to find f prime is to take the antiderivative of f double prime. So f prime of x is the integral of the second derivative, or x. Okay? So we know that that's x squared plus 2, or sorry, x squared over 2 plus c. That's f prime of x. That means that f prime of 0 just equals, if we put in 0 for x, just equals c. But we also know that f prime of 0 equals 1, so that means that c equals 1. So that gives us a particular solution for f prime. It's x squared over 2 plus 1. Now, to find f, I have to take the antiderivative of f prime. So the integral of x squared over 2 plus 1 with respect to x. So here I'm looking at 1/2 integral of x squared dx plus the integral of 1 dx. Well, this here, that's going to be x cubed over 3. Got to put that 1/2 back on. The antiderivative of 1, of course, is just x, because the derivative of x is 1, and I have my constant of integration. Simplify here, I end up with x cubed, sorry, getting ahead of myself, x cubed over 6 plus x plus c. This is f of x. All right? Now I know that f of 0 equals 0. And using this expression, I also know that f of 0, well, that's going to be 0, that's going to be 0. F of 0 is c, and f of 0 is 0, so c equals 0, and my particular solution is x cubed over 6 plus x. And that's how we use antiderivative to solve differential equations.